What's up, everyone? Today, we're going to create the interaction diagram for the column as shown and evaluate whether the applied loads are acceptable. If you haven't watched the previous lecture on this topic, I recommend checking the link in the description below. The column is loaded with 1423.1 kilonewtons of compressive force and 104 kilonewton meters of bending moment. Section dimensions, material properties, and even a trial arrangement of rebars are already provided. All that's left is to check whether the section, along with its reinforcement, can safely carry the loads by considering the interaction between axial and bending stress. Let's begin. Now that we've introduced the problem, here's the general outline of our calculation process. Based on the previous lecture, our first step is to assume a rebar layout. Next, we'll group the elements, solve for the plastic centroid, determine the key points, and finally construct the interaction diagram. Since the first step is to assume a rebar layout, let's talk about that. In most cases, we're given only the bare section, no reinforcement yet. It's up to us to propose a favorable rebar arrangement based on how the section is expected to behave under stress. But in this example, the layout is already provided. So instead of assuming, we'll use the given layout and proceed to check whether it performs well. With the rebar layout in place, the next step is to group the elements. We group concrete and steel components based on their alignment, specifically whether they lie perpendicular to the direction of the bending moment. In our case, we'll define 4 groups. Group 1 is the concrete section itself. Group 2 includes the rebars on the left side of the section. Group 3 is for the rebars at the middle, and Group 4 consists of the rebars at the extreme right. These groupings will help us analyze how each part contributes to the axial capacity of the section. Now that the groups are defined, we can solve for the plastic centroid. Since the section is symmetrical in both its shape and rebar layout, we can say with confidence that the plastic centroid lies at the geometric center. That is, halfway across the width of the section. So for a section width of 500 mm, the plastic centroid is located at 250 mm from either edge. But let's not just assume. Let's prove that the plastic centroid is indeed at 250 mm. We'll start by identifying the location of the maximum compression fiber. This is the edge of the section that's most compressed by the moment. With the maximum compression fiber identified, we now compute the capacity of each group. Group 1, the concrete contributes compression. Its capacity is calculated as the strength of concrete multiplied by its area. In this case, the full section area. Groups 2 to 4 are the steel groups. Each is assumed to be under compression, and their strength is based on the yield strength of steel multiplied by their respective rebar areas. Note that for compression rebars under yielding condition, the stress is equal to Fy minus 0.85 times Fc prime. Now we substitute all known values into our expressions for group capacities. Here are the outcomes of the calculations. Each group's axial capacity has now been determined. Next, we determine the distance of each group's centroid from the maximum compression fiber. We'll name them as D1, D2, D3, and D4. After plugging in all values, these are the computed distances from the maximum compression fiber to each group's centroid. Now we calculate the moment about the maximum compression fiber. We multiply each group's force by its respective D value and sum them all up. This total moment is what we'll refer to as M. Let us not forget to get the sum of all P as well. Finally, to get the plastic centroid, we divide the total moment M by the total force P. That gives us the precise location of the plastic centroid. And as expected, the value confirms our earlier assumption. The plastic centroid is at 250 mm. With that established, we're now ready to create the interaction diagram. In our previous lecture, we said that there are 11 key points in a full interaction curve. However, for simplicity, you can reduce it to 6 points in some cases. For this example, though, we'll solve all 11. We begin by preparing a table with all 11 points. We'll also add two important columns, one for Pn, that's the axial capacity, and one for Mn, the moment capacity. Let's start with point 1. Here, Pn1 is simply the total axial capacity from our plastic centroid analysis. The corresponding Mn1 will be 0. This represents pure compression without bending. For point 2, we need to solve for a few parameters first. Beta 1, the area of a single bar, and the strain at the balanced condition. To compute the coordinates of point 2, we begin with the code-based condition. This point corresponds to the maximum axial load allowed under NSCP C101-15, section 422.4.2, or ACI 318-11, section 10.3.6.1 and point 2. Under this provision, the axial load Pn2 is equal to 0.8 or 80% of Pn1. The corresponding moment Mn2 is unknown, and that's what we aim to compute. We can use the first method, which involves assuming a value for the neutral axis depth c and adjusting it until the computed axial force matches the target. Here are the key assumption zones. First, when c is between 440 and 500 mm, this means all rebars are within the compression block, so all groups act in compression. What we need to determine is whether each group yields or not, depending on how far it is from the compression edge. Next, C equals 440. Here, the compression block is exactly at the steel on the left side. This is a critical point where that group be on the verge of transitioning to tension. We can keep changing the location of C when the previous assumptions are failing. By testing values of C within each of these zones, we can check which assumption leads to a force that satisfies the 0.8 Pn condition. Now for the second method. Instead of trying values manually, we can set up an Excel spreadsheet where all computations, concrete capacity, steel stress, yielding status, are driven by a single input cell for C. Then, by using Excel's goal seek, we let the software find the most accurate value of C that satisfies the Pn condition. This makes the process faster and avoids multiple iterations. Let's try to use the first method by trying the first assumption where C is between 440 and 500 mm. Here, all rebars are within the compression block, so we are assured that they will be under compression stress. What's left for us to do is check whether the rebars yield or not. Instead of guessing the conditions, we set a trial value for C based from the condition of our assumption. We start with group 2 and we let C be equal to 450. Note that the stress for a compression bar is equal to 600 times C minus D divided by C. Using the Fs formula, the resulting stress is 13.33 megapascals, much lower than Fy, so group 2 does not yield. We apply the same process to group 3. With C at 450, the stress is 266.667, still less than Fy, so group 3 also does not yield. Now, for group 4, the stress here exceeds Fy, which means this group will yield. With all steel groups classified, we now assemble the complete expression for Pn. We include group 1, the concrete, always in compression, so its force is 0.85 Fc prime times A times B, and group 2, the steel on the left, in compression, but not yielding, so we use the non-yielding Fs formula. Group 3, the middle steel, also compression and not yielding, same formula applies. Group 4, the rightmost group, compression and yielding, we use Fy. And remember, for all compression steel, we subtract the displaced concrete stress, 0.85 Fc prime, from Fs to get the net force contribution. We then sum up all 4 group forces to complete the expression for Pn under this condition. Now we plug in all known quantities. The only unknown left is C. Solving gives us C equals 513.858. That falls within our assumed range, so our assumption is valid. Just to confirm, let's try another assumption. Understand that we are only doing this just to show how to deal with column conditions when our initial assumption failed. Since we have already proven that the previous assumption is correct for this problem set, we could just stop there and use the computed C. But anyway, let's try the other assumptions. This time we assume that C lies between group 2 and group 3, meaning greater than 250, but less than 440. Looking at the section, we can already tell that group 2 is in tension since it's outside the compression block. Groups 3 and 4 are still in compression. We choose C equals 400 for this trial. Now let's compute stress for group 2. Since it's in tension, the formula becomes 600 times D minus C over C, and we assign the result a negative sign. The outcome is negative 60 megapascals, which is below Fy, so it does not yield. Note that the negative sign is consistent with our established rule from previous lecture that tension is considered negative. Group 3 is in compression, and the result of the calculation is also less than Fy, so again not yielding. Group 4 remains in compression, and its stress reaches Fy, so it's yielding. With the yielding behavior confirmed, we now write the equation for Pn again. Group 2 is tension, not yielding, and Group 3 is compression, not yielding. Group 4 is compression and yielding. We apply the appropriate formulas and subtract the displaced concrete stress as needed. After substitution, we solve again, and this time the resulting C doesn't fall within our assumed range. So the second assumption fails, and the first one is proven valid. Now that we are confident about the value of C, 513.858, we can solve for the moment Mn. To do this, we take the force in each group and multiply by its distance from the plastic centroid. That's dp minus d. If the result is negative, it just means the distance was taken in the opposite direction. We simply reverse it. We already know C, so we can solve for A, and then calculate the force for each group. The outcome is 192.498. And with that, we've completed point 2 of the interaction diagram. This time around, let's solve for the value of C using goal-seek in Excel. Using a new file and a sheet, type the following labels in the same cells as shown. Just after row 15, you'll see that we have a table. This table will be used to calculate the properties of each structural element. Notice that there are 4 groups, which correspond to the 4 element groups, 1 concrete and 3 steel groups. Identify all of the items already given, or have already been calculated previously, and encode them in the sheet in an orderly manner. Here, what we'll be doing is to encode FC prime, Fy, dB, DSCC, beta 1, dt, and dp under column C, starting from row 2. And then we'll provide initial value at C under cell C11. For now, 1 will be okay. At this point, we will have to modify our template so that it will perform automatic calculations as the value of C is changing. Starting from A, it must be calculated in terms of the value of beta 1 and the value of C. So the input formula will be equals C3 times C11. Take note that the data of columns C, D, and F of the table, which correspond to B, H, and the center, will be used for the concrete elements. For concrete group 1, B is constant at 300, so we will just encode it as such. H, on the other hand, will vary depending on the value of the compression block. A, the input will be a formula equals C12, meaning the H of concrete group 1 is equal to the value of A. The center of group 1 will be half of its height, so the input will be a formula D15 over 2. The area of any of the concrete groups will be the automated product of B, and the H under the column area, we encode the formula equals C15 times D15. For all of the steel groups, we will use the same area, since all of the group only comprise of 2 20 mm diameter rebar each. We could either hard-code the value or compute through Excel itself, like what is shown in the screen. The centroid D of the concrete group will be the value of the column center under column E, so we will allow it to copy the value into D using the formula equals E15. The centroid of the steel groups will not change. They are the values of the previously computed Ds, D2, D3, and D4. We'll just type them as numbers. dP minus d represents the distance of each group from the plastic centroid of the section. The formula for the first group will be equals C9 minus G15. It is important to remember to lock the address of dP, which is C9 using $symbol, to ensure that the address will not change if we copy the cell to the lower cells within the same column. And to quickly copy the formula under H15, select cell H15, then find the fill handler. The fill handler is the small square solid box at the bottom corner of the cell selection box. Click the handler, then drop it until H18, and then release. Click on the copied cells to check if the formula were copied properly. Let us now create the computation for the stress in each group. The first group is a concrete group, so we'll use the formula 0.85 times Fc prime. The formula will be equals 0.85 times C2. The address of Fc prime may be locked in case we want to copy it to other cells using the $sign. The stresses on each steel element is a bit complicated because the behavior of steel may either be under compression or tension. It can also be either yielding or non-yielding. Steel will be under tension if it is outside the compression block, which is the same as saying D is greater than C. If the neutral axis is at the location of the rebar, then the stress is 0. This is also the same as saying D is equals C. While if D is less than C, or if the rebar is inside the compression block, the steel is under compression. We visualize the input by creating a representation of the formula. Here you'll see a pattern of nested if functions. The first condition is for compression, while the second is for D equals C. And then we will place the outcome of tension if the second condition is false. The formula for the stress of compression will be Fs prime minus 0.85 times Fc prime. The value 0.85 times Fc prime is for the displaced concrete, and the value of Fs prime is 600 C minus D all over C, but must not exceed Fy. We'll use min function to make sure that this condition is applied. On the other hand, the formula for the stress of steel under tension will be negative Fs. The negative sign reflects the assumption that tension, stress, or force is negative. The value of Fs is 600 D minus C all over C, but must not exceed Fy. Just the same, we'll use min function to make sure that this condition is enforced. Be advised, the negative sign should be placed outside the min function. Replacing the compression and tension with the appropriate formula in the base if function, the result will be as shown. Let us focus on the second element. The first steel group, we convert the base if function into an Excel formula by replacing D with the address of D of the second element, that is G16. Then C is replaced by the address C11, then Fy replaced with C3, and Fc prime with C2. After then, we will lock the values of Cf prime and Fc prime using the $symbol. Same thing will happen for the rest of the steel groups. So we'll select the stress of first steel group in cell I16. We then grab the fill handler and drag it until I18. At the moment, the values are not appropriate as we have just initialized the value for C equal to 1. When we eventually use goal seek, these values will change. The force P for any of the elements will be computed using the same formula. Under the first group J15, we encode the formula equals F15 times I15. We can copy the formula to the other cells by grabbing the fill handler until the row of the last group. The moment, on the other hand, M, is computed by multiplying the force with the moment arm. The formula can then be copied to the other cells of the other groups using the same approach as using the fill handler. At the bottom of both the force and moment column, we encode formula to get the total of each column. The total of P and M will be the values of Pn and Mn. We may refer to these values in other cells like the one being shown. If we format this properly, we can easily copy the values to be transferred to other documents like computation reports. This will also serve as our visual indicator during the process. At this point, we are now ready to initiate the trial and error process. Let us select the total of P, which is J19. We then open data in the menu bar. Under What If Analysis, we select Goal Seek. The Goal Seek window will appear. Since we have already selected cell J19, the set cell input box has the address J19. If in case the set cell has the wrong address, we can manually edit the value. The to-value input box will be the value of the target PN value. In this case, it would be 80% of PN1. We already have the value from previous calculation, that is 4048717.552. We replace the input box by changing cell with the value of the address of C. This would be C11. Click OK to begin the iteration. Now, when the iteration concluded, meaning the goal seek status says it found a solution, check if the target value and current value matches. If not, then press OK and repeat the process. If target and current are the same, we press OK to finalize the result. This goal seek process revised the value of C multiple times so that the value of Pn will match the target value we are after. Here, the value of C is the same as the value we have obtained from the other method where we assumed values. One of the primary benefits of utilizing Microsoft Excel for data analysis is its capacity to execute multiple calculations concurrently with remarkable efficiency. For example, other than solving for C, we are also able to solve for other values such as Mn within a single spreadsheet. Furthermore, the true value of Excel becomes evident in its ability to support reusable templates. This template we have just created can be applied consistently to subsequent computations that follow a similar framework. This reusability not only enhances operational efficiency, but also ensures uniformity and accuracy across our analyses. By leveraging such a template, we can significantly reduce the time required to set up new calculations, allowing us to focus on interpreting the results and deriving meaningful insights from our data. We're now ready to move on to point 3. As we've learned in the previous lecture, the process for calculating points 3 to 9 follows the same steps. We solve for the value of C based on the steel strain defined for each point, and for point 3, the strain is 0. To calculate the value of C, we first identify the depth of the rebar that's farthest from the maximum compression fiber. This depth is represented by dt. The value of C can then be computed using this formula. 0.003 times dt divided by the quantity 0.03 plus the steel strain, epsilon s. So for point 3, since epsilon s is 0, the formula simplifies to C equals 440 mm. We now add an extra column to our table to store the values of C. This is where we'll place all the computed C values for points 3 to 9. Let's proceed to solve the steel strain values for points 4, 5, and 6. Each of these has a defined strain value which we'll use to compute C. Once we've solved the steel strains, we can now proceed to compute the corresponding C values for points 4 through 9. We'll still use the same formula. 0.003 times dt divided by the quantity 0.003 plus epsilon s. This formula works for all remaining points. Applying the formula, the computed values of C for points 4 to 9 will be as shown. We then store these computed values of C in our table, one row for each point. Now we add another column for the value of A. Using the C values we just calculated, we solve for A from point 3 to point 9. Each value of A is simply beta 1 times C, and here are the resulting values for each point. Finally, we store all the A values in our table, completing this part of the setup. If we visualize the size of the compression block at each point, The following illustrations help show how it changes. As the value of C varies from point to point, it directly affects the stress behavior in the rebars and the extent of the concrete compression zone. With that, we can now assemble the computations for axial loads and bending moments for each point. For the axial load, we sum the contributions from each element group, that is, the total Pn from group 1 through group 4. For the moment, we multiply each force by its distance from the plastic centroid, so the general formula for moment becomes P times the quantity dP minus d. Let's begin with group 1, the concrete compression block. The formula for its force is 0.85 times Fc prime times A times the width of column B. Take note that Fc prime and B are constants, while the value of A will vary depending on the point. After performing the computation, here are the resulting force values for group 1 at each point. We now update our table by replacing the force values for group 1 across all points. Let's move to group 2. This is the group of steel bars located at the leftmost edge of the section. For each point, we need to identify whether the rebar is under tension, compression, or experiencing zero stress. At point 3, the value of C coincides with the location of group 3 rebars. That places them on the neutral axis, meaning zero stress. From points 4 to 9, group 2 rebars fall outside the compression block, shown by the shaded green area, indicating that they are under tension. For tension rebars, the formula becomes area of rebar times the negative value of the smaller quantity between Fs and Fy. We use the smaller of the two to determine if the steel yields, and for tension, Fs is computed as 600 times d minus C divided by C. We now substitute all known values into the equation for each point. The resulting force values for group 2 are now available for all points. We then update our Pn and Mn calculations by inserting these group 2 force values into each of the equations. Now let's proceed to group 3. The rebars are located near the middle of the section. From the shaded compression blocks for each point, we observe that at points 3, 4, and 5, group 3 rebars are inside the compression block, meaning they act in compression. From points 6 to 9, they lie outside, meaning they transition into tension. For compression rebars, the stress is the smaller of Fs or Fy, minus 0.85 of Fc prime. The formula for Fs in compression is 600 times C minus d over C. We multiply this stress by the area of steel to compute the force for each point. Let's now substitute the known values into the equations. These are the computed force values for group 3 across all points. We now update the Pn and Mn calculations again by inserting group 3 forces. Finally, we move to group 4, the reinforcements on the rightmost side of the section. Based on the shaded concrete compression region, group 4 remains entirely within the compression zone for all points. So we will use the same compression formula again for this group. After performing all computations, here are the resulting forces for group 4. We now complete the Pn and Mn computation by inserting all group forces from group 1 to group 4. We evaluate all computed values of Pn point by point. Next, for the bending moment, we plug in the distances, dP and d values for each group. The value of d1, which is the center of the concrete compression block, is A divided by 2. Meanwhile, d2 to d4 are the constant rebar depths from the extreme compression fiber. These stay the same for all points, even as C changes. We now evaluate all Mn values across the table. At this point, we've computed both Pn and Mn for all points, and now we just store all values in the same table as we've used before. Now here's a time-saving option. Instead of calculating PN and MN manually, we can use the Excel spreadsheet we prepared during the goal-seek setup for point 2. With all C values already known, we can simply input them one by one into the Excel sheet. The corresponding PN and MN values will be computed automatically. We can now move on and compute the forces in point 10. So just like in point 2, we have a known value for Pn, but unlike point 2, where Pn is 80% of Pn1, the value of Pn in point 10 will be equal to 0. With that in mind, we will find the value of its pair Mn using trial and error approach or using Excel goal-seek setup. Now for point 10, I will only show the solution when using goal-seek, using the same spreadsheet we've been using so far. Let us perform the calculation. As you can see, the current value of C is the value of C for point 9 when we repeated the calculation of Pn and Mn using the spreadsheet. So in order to perform goal-seek, we select the cell of total Pn. Here, that would be cell J19. We then open goal-seek through data in the menu bar and the what-if analysis option. The set cell would be the address of the total Pn. We then assign 0 in the toValue input box. This is the target value of Pn. The input box, by changing cell, will contain the address of the cell that contains the value of C, that is C11. Then press OK to initiate iteration. As you can see, the target and current value might not be exactly the same, but close enough. The result of Mn is also available, that is 163.811. We tabulate the results for easy referencing when constructing the illustration. Side note, in case you encountered a situation where the Pn of point 9 is negative, you'll have to swap the position of point 9 and 10. 10 becomes 9 and vice versa. Let us proceed with the last point, point 11. The coordinate of this last point is a pair of pure tensile axial force and 0 moment. The value of the axial force is obtained from the capacity of all of the rebars acting as a single unit to resist the stress, while considering that the contribution of the concrete section is non-existent. So, the formula would be the area of 6 bars times the yield strength of the steel. And so that would make the table of Pn and Mn complete. We shall then add another column for the strength reduction factor, phi. And, knowing the characteristics of each point, let us fill up the known values of column phi. Points 1 to 5 are all cases where the column is under compression-controlled condition, so the value of phi would be 0.65. Points 8 to 11 are known to be tension-controlled, so the strength reduction is 0.9. What's left for us to do is solve for the strength reduction factor of the transition zones, points 6 and 7. Let us then arrange the columns of the table and add another sets of columns for the values of the ultimate axial and bending. We multiply the strength reduction factor and the values of Pn and Mn to get Pu and Mu. From the tabulation, we build the interaction diagram, and the result is as shown. If we draw a line from the origin to point 5, that sets the boundary for compression-controlled sections. So anything within the red zone is safe and is classified as compression-controlled condition. Similarly, a line can also be drawn from the origin towards point 8. The zone between that line and the horizontal axis is the tension-controlled zone. It is still considered safe for the axial force and moment to fall within this zone, but it would not be recommended because this indicates that the bending moment is much more dominant in terms of its effect on the designed column section. If that is the case, it is best if the section is redesigned. The zone in between red and green is the transition zone. Areas anywhere outside the shaded regions are all considered unsafe and would require redesign of the section or rebar arrangement. Now let's plot the applied load onto the interaction diagram. As shown, the load falls well within the compression-controlled zone, indicating that the section is safe under the given conditions. But if we take a closer look, there's a noticeable margin between the applied load and the failure envelope. This tells us that the column's capacity significantly exceeds what's actually required. From an efficiency standpoint, this might be too much capacity. So, if economy is a design priority, the section can be revised, possibly reduced, to better match the demands without compromising safety. But for now, based on the current analysis, we conclude that the column is safe. And that wraps up our lecture. And if you found this helpful, consider giving the video a like and subscribing to the channel for more lectures like this. Feel free to leave any questions or insights in the comments. Thanks for watching, and I'll see you on the next one.